Before the digital age, controlling electricity meant using physical motion. Large mechanical switches, known as relays, had to snap open and closed to manage data. But physical motion has a major weakness. Moving parts always fail. Over time, metal contacts bend, sparks fly, and heat can eventually weld the whole system shut. The first computers, such as the ENIAC, filled huge rooms using thousands of these parts and glass tubes. They broke down almost every day. Back then, a system failure often meant looking for an actual bug, such as a moth stuck inside a machine. Today, your phone holds billions of tiny switches that never wear out. This is the power of solid-state technology, fast switching with zero moving parts. How did we do it? We stopped moving big pieces of metal and started to modify the atoms inside a simple grain of sand, silicon. But how do we turn sand into logic? Welcome to VastVoltage. Let's visualize the invisible. Just like carbon in a diamond, silicon has exactly 4 electrons in its outer shell. To reach a stable state, these atoms seek to have 8. Their solution is to share. When billions of silicon atoms bond together, they form a perfect 3D atomic grid, a crystalline lattice. Every single atom bonds with 4 neighbors, sharing its electrons in what we call covalent bonds. In this pure natural state, every valence electron is occupied. None are free to move. This is why pure silicon is an insulator at low temperatures. But for this to work in a high-tech lab, the silicon must be near perfect. The material must be almost 100% pure. If even one atom in a billion is an intruder, the electrical behavior becomes unpredictable. This extreme purity is why silicon ingots are the most precise structures made by man. However, silicon has a distinct weakness: heat. As the crystal gets warm, the added energy makes the atoms vibrate intensely. Eventually, this shaking snaps a covalent bond, setting an electron free. This leaves behind an empty spot, a hole. If the chip gets too hot, it leads to a thermal runaway. If too many electrons break free by accident, the silicon becomes an uncontrolled conductor and the chip melts from the inside out. This is why your computer needs active fans or liquid cooling. But we don't want to use heat for control. We need the precision of atomic engineering. To make silicon useful, we must change its behavior. We precisely modify the crystal grid by adding a tiny amount of specific elements. This process is called doping. First, we introduce an atom of phosphorus. Unlike silicon, phosphorus have 5 valence electrons. When it enters the grid, 4 of its electrons bond perfectly with their neighbors. But the 5th electron has no bound to hold it. This extra electron becomes a free charge carrier, unattached and ready to move. Because we have added negative charge carriers, we call this N-type silicon. In this setup, phosphorus acts as a donor, giving away its extra electron to the system. On a different piece of silicon, we do the opposite. We inject an atom of boron. Boron only has 3 valence electrons. When it joins the grid, it is missing a bond. One spot remains empty. We call this vacancy a hole. Here is the key to the digital age. If a nearby electron jumps to fill that empty spot, it leaves a new hole where it used to be. As another electron jumps, the process repeats. While the actual electrons move one way, the hole appears to move in the exact opposite direction. In engineering, we treat these holes as real physical particles with a positive charge. Because this material is now full of these moving positive spots, we call it P-type silicon. Here, boron acts as an acceptor, looking for electrons to fill its vacancies. Even though both blocks are still electrically neutral, we have completely changed how they work. We have created a surplus of mobile charge carriers. Now the stage is set for the most important part. The magic happens when we join them together. We take a block of N-type silicon packed with free electrons and fuse it to a block of P-type silicon full of moving holes. The free electrons on the N side look across the boundary and see millions of empty holes on the P side. They rush across to fill them. When a negative electron meets a positive hole, they recombine. As a result of this recombination, the area near the junction is emptied of all mobile charges. With no free electrons or holes left to move, these regions become non-conductive. We call this the depletion region. But something deeper is happening. As the electrons leave the N side, they leave behind positive ions. As they fill holes on the P side, they create negative ions. This buildup of charged ions creates an internal electric field, an invisible wall that pushes any new electron back. The two sides reach a state of equilibrium, permanently separated by this barrier of pure electric force. Our material has suddenly become an insulator again. We have just built the P-N Junction. It is the foundation of every electronic device on Earth. So we built a wall. But how do we control it? We apply an external voltage from a battery to manipulate the depletion region. If we connect the positive end to the N side and the negative to the P side, we pull the electrons and holes away from the junction. This causes the depletion region to expand, making the barrier wider and stronger. No current can pass through. In digital logic, this state of absolute blockage represents a logic zero. The switch is off. We call this reverse bias. But this wall is not invincible. If the reverse voltage is pushed beyond its limit, the barrier suffers an avalanche breakdown. The internal structure is forced open, and the junction can be permanently destroyed. But watch what happens if we flip the battery. Now we are in forward bias. We push the electrons and holes toward the center, squeezing them against the barrier. If our push is strong enough to overcome the internal potential barrier, which is about 0.7 volts for silicon, the barrier suddenly collapses. The blockade is crushed, and a massive ocean of current flows through the material. In the digital world, this is a logic 1. The switch is on. This one-way valve is what we call a diode. It is a vital tool, but the real magic happened when engineers added a third layer, creating the transistor. Think of a transistor as an NPN structure. We have three main zones: the emitter, which is the source of electrons, the collector where the electrons want to go, and a very thin middle layer called the base, which acts as a gatekeeper. To make this work, we use two separate circuits. First, a powerful main battery tries to push a massive amount of electrons from the emitter to the collector, but they are completely blocked by the base layer in the middle. Then, we connect a second, much smaller battery directly to the base. By applying a tiny voltage here, just enough to cross that 0.7 volt threshold, we flood the base with charges. This instantly collapses the internal barriers. Suddenly, the massive current from the main battery can flow through the entire device. You might ask, isn't this just a tiny switch? Yes, but with a superpower. A mechanical switch is binary. It is either fully open or fully closed. A transistor, however, is proportional. Think of it as a precision valve. The tiny current we inject into the base doesn't just flip the switch. It controls the exact size of the opening. If the base signal increases by a tiny fraction, the massive flow from the battery increases by the exact same ratio. This is amplification. It allows a weak signal, like the vibration of a microphone, to dictate the shape of a massive wave of power. In a computer, we simply push this to the limit, using that tiny base signal to slam the gate between fully blocked and fully open. This creates the lightning-fast ones and zeros of the digital age. We have successfully turned a simple stone into logic. By modifying the atomic design of silicon, we created microscopic gates that open and close billions of times every second with zero moving parts. This is the foundation of every CPU, smartphone, and AI system. Today we use light to print these structures onto silicon wafers, shrinking them so much that the internal barriers are now only 3 to 5 atoms thick. At this extreme scale, the laws of classical physics break down. Electrons begin to behave like waves. They can simply tunnel to the microscopic walls and appear on the other side even when the switch is supposed to be off. This is quantum tunneling. It creates massive heat and data errors, and it is the greatest physical barrier modern engineers are trying to overcome today. But even the fastest CPU is dead without a push. We used a specific number, 0.7 volts. But what is a volt exactly? It is a force, it is energy, or it is something far more fundamental. We call it voltage. We will decode its true hidden nature. If this video helped you see the world in a new way, make sure to subscribe, like, and drop a comment to join our mission. Mastering engineering starts with visualizing the invisible. I am VastVoltage. See you in the next one.